So thank you very much. I would like to first thank the organizer and in particular Professor Yao for inviting me, giving me this opportunity to present our work here. And also I must say that I really enjoyed this conference, very broad, a lot of topics, and wonderful hospitality here. So I'm very happy to be here. And so I will be talking. Also, I would like to thank Mauricio, who, so I prepared slides actually, but in the last minute, since the previous speaker dared to give a Blackboard presentation, and I always enjoy Blackboard presentations, so I decided 5 minutes ago to actually switch. So, but you will find online on the website, I guess, the slides. So I will, of course, say much less than I had intended to, but you can find kind of the transcript and all the details on the slides, which are on the website. And so, yeah, I will try to explain what I mean by the atoms of moduli space of supersymmetric vacuum. And so, first of all, as a motivation, my motivation here is to answer a question: how to characterize a QFT. So quantum field theory, so this is part of this very big question: what is quantum field theory? Which is incredibly difficult to answer. And in order to characterize or how to define a QFT, there are many ways to do this. And the standard way, the most natural one, and also historically the first one, is using, well, as the name indicates, you specify quantum fields. Specify what are the fields, and then you specify what are the interactions. And typically, this is done using Lagrangian. So that's very nice, and it's very powerful to describe the standard model. The problem is this is a definition which, first of all, can be ambiguous in the sense that two QFTs could be the same, but could be described with very different quantum fields. So if we think of Yang-Mills theory, we can describe it in terms of quarks and gluons, but we can also describe it in terms of baryons and mesons. And these are equivalent descriptions. So one way of writing Lagrangians is using, for instance, specifying a gauge group, and then, but also the gauge group is something which is not intrinsic of the definition. So this is not intrinsic. And also, it might not exist. So first of all, it might not be very convenient if you are dealing with a strong coupling, with a strongly coupled theory. But more than that, it might not exist. We now know that they are intrinsically non-Lagrangian QFTs, in particular in the supersymmetric world. So the goal of this talk is to advocate for another way of characterizing. So it will not really be a definition, but rather, one could specify invariance. So what do I mean by invariance? I mean quantities. So the simplest kind of invariance are numbers, or more generally combinatorial objects. So we will see that we will actually deal with combinatorial objects, but the simplest kind of combinatorial object is a number, integers, for instance, or groups, which are really independent of your description. So an example of this is if you have, for instance, global symmetry. So I just said that gauge symmetry is something which is not intrinsic, but global symmetry is intrinsic. And you can describe it in the old-fashioned way with some group, or maybe in the modern way with higher form symmetries, maybe categorical symmetry. So this is one kind of combinatorial object. If you have global symmetry, you can also give anomaly, coefficients, etc. Central charges, and so on. So that's one thing. And here, I would like to advocate for another thing, which is the singular structure of the moduli space of vacuum. So this is something that is less familiar, probably. And I would like to, in this talk, to present what we can learn from that and what we can compute, and first of all, what it looks like. So, of course, depending on the theory, this might be more or less rich. Maybe there is no moduli space of vacua. If there's a single point, then there is not much to say. So the first thing is that I will restrict my attention to not the most generic QFT, but I will restrict to a particular class with supersymmetry, and even I will impose a conformal invariance. So in the rest, maybe I write here. So from now on, I will focus on 8 supercharged, superconformal field theories in dimension 3, 4, 5, and 6. Why do I pick this particular class of theories? Because the superconformal algebra contains a bosonic factor, which is an SU2 R. So the R symmetry in all these dimensions, the 8 supercharged superconformal algebra always contains an SU2R. And this SU2R allows to define in a completely abstract way what is one part of the moduli space of vacua, which is the Higgs branch. So this allows to define the Higgs branch. So what is the Higgs branch? The Higgs branch is the part of the moduli space of vacua on which this SU2R factor acts, but no other factor of the R symmetry acts. So if you think in terms of 4-dimensional, so a particular case is 4-dimensional n equal 2 superconformal algebra, then you have an SU2R and also a U1. And you can partition the moduli space of vacua into the part on which this U1R acts, and you would call this a Coulomb branch, and the part on which the SU2R acts, and this is the Higgs branch. And then there is also the part in which both act, this would be some mixed branches. So the Higgs branch is what I will focus on here. So just to summarize, and then I will give some examples. Here is the picture. We have a certain SCFT, which is sitting here, very complicated object. And then from there, I extract something. So my goal is to extract an invariant, something which does not depend on the way that this is defined. And this invariant will be the singular structure of the Higgs branch. So what is this? Let's first give an example, and then it will become clear. I will write what the general thing is. Well, okay, let me just draw what it looks like. So the Higgs branch is a variety. It will be an algebraic variety with a certain structure, and in the second part of the talk, I will describe more about the geometry. This is a singular variety, and so you can compute the singular locus. And the singular locus, in general, itself is singular. So then you can compute the singular locus of the singular locus, and you can proceed like this recursively. And by doing so, you obtain a stratification of the Higgs branch in terms of more and more singular loci. And this will be the set of singular loci is usually a finite set, which is partially ordered. And this partial order you can represent with a Hasse diagram. So that represents which singular stratum is contained in which other singular stratum. So it will be some kind of diagram like this. Okay, let's draw some diagram. So each dot is a singular stratum, and the lines indicate which one is included in which one. What do I mean? That's right. Okay, but here, in order to be a bit more specific, and because I wanted to use superconformal algebra here, but yes, that's right. This is a bit more general. I will not do the most general thing, but I can, yes, but I was not. Yeah, I mean, yes, it can be more general than that, but yeah. So let me give an example to make this a bit more concrete. So let's look at a particular four-dimensional n equal 2 theory, and I define it using this language here. So I will say that there is a gauge group. So let's say I take SU3 to be a bit like in the standard model. So SU3 gauge group. And then let's add a number of fundamentals. Let's put 6 like in the standard model. So 6 quarks. But of course, these are supersymmetric versions. So this matter content and gauge group, I can denote using a familiar quiver notation. I put an SU3 here and 6 hypermultiplets. Now, the Higgs branch of that theory is really defined. This is a theory that you can analyze classically, and that's just the Higgs mechanism. And so the way to analyze this theory is as follows. So there is a Higgs branch. So let's draw the Higgs branch, something like that. And then it has so on the Higgs branch, the fields take vacuum expectation value, and they completely break the gauge group. So on the generic point here, the gauge group, which was SU3, is completely broken. So broken SU3. Then there is a point at the origin. Let's put a yellow dot here. That's the origin. And here, SU3 is preserved. But then there is an intermediate locus. Let's put it in blue. Something like that. And this is where there is partial Higgsing. So let's say out of SU3, SU3 is not fully broken. Let's say it's broken to SU2. So that's exactly what I mean by this stratification. And it turns out this change of gauge group corresponds to a phase transition, which is a Higgsing phase transition, and they correspond to singularities because phase transition is associated to degrees of freedom, which were massive at a generic point, and they become massless when you approach a singularity. So there are two kinds of phase transitions here. There is the phase transition when you go from the non-Higgs, from the fully Higgs phase to the partially Higgs. So here there is a phase transition when you approach the singular locus from here. And then there is another phase transition when you move on the blue locus towards the origin here. And so this picture, instead of drawing this geometry, I want to extract the combinatorial nature of it. And so this picture I will denote as this by I put one white dot for the full Higgs branch. I put one dot for the blue locus here, and then one dot for the most singular part where there is no Higgsing. And then there are transitions which tell me what fields become massless. And so I can denote this one here by blue line. This is these blue arrows here. And then one by red. So this picture is the combinatorial data associated to the Higgs branch. Now, this is not it does not contain much information. It's just 3 dots connected by a line. So I want to decorate this diagram with information. The information that I want to include is what is the geometry corresponding to these phase transitions, because this geometry tells you about how fields become massless, and so they in this particular case, they tell you how the gauge group is broken. So the way that this works is as follows. Here, for instance, when you're on the, let's say that the red part here, it would correspond to the full Higgs branch of just an SU2 theory. You see, you don't know that there is an SU3. If you look locally around here, that's exactly the Higgs branch of the SU2 theory. So if all of this is the Higgs branch of the SU3 theory, SU3 with 6 fundamentals, that part here alone would be, let's put it in red, would be the Higgs branch of SU2 with, it turns out, with 4 fundamentals. And then you might ask, is the blue line also the Higgs branch of something? And you can compute, this is just algebraic computation. It's very easy because it's all Lagrangian and there is nothing mysterious here. You can compute, it's an exercise. Mauricio gave exercises, so I also give exercise. It turns out it's the Higgs branch of U1 with 6 flares. And so you see, by doing this, I have broken my theory, so not all the theory, but some aspect of the theory, I have broken it into 2 parts. In a way, this is made out of this plus this. So, well, actually, that's right here. Okay, I should have. But actually, if you consider it as a 3D theory, then there is it flows to a 3D SCFT, so actually, still fine. But it's true in 4D. So, so this is the way that I break the thing in 2 pieces. And these are the things that I want to call these atoms. And they are these atoms of moduli spaces. Why are they atoms? Because I cannot Higgs more. You see, these are rank 1 groups. So these are the things which are not more Higgsable. The thing is, you might say, okay, that's a bit trivial, because in the end, you just need to find what are all the rank 1 gauge groups, and that's it. The problem is, it's not a problem, it's the reason we are doing all of this, is that this applies, the same applies in the strongly coupled regimes, where you would not have, for instance, some gauge theoretic description like that. So, for instance, in 4D n equal 2, you can also define class S theories, which are defined, as you probably know, by some Riemann surface, punctures, and so on. And you might want to do the same thing. And there, it's much less clear what is, I mean, there is no gauge group and so on. But still, you can define a Higgs branch, as I explained here. And the Higgs branch will be some space like this with a singular stratification. And then you might ask, what are the building blocks? Except I can no longer use these gauge theory recipes, which are classical algebra. So for this, we need to dive into geometry. And so now I will turn, in the second part of the talk, to the geometric structure which underlies all of this. So let's put it here. Okay, it's difficult to relate here. So the geometry, what is the geometry? The goal is to replace those things which, as I said, are non-intrinsic descriptions by really just saying what is the geometry of those singularities. So there is a general consequence of supersymmetry, which implies that Higgs branches are hyperkähler. But of course, hyperkähler, if you look up the definition, you need to have a smooth manifold, and then to have a metric which satisfies the properties of hyperkähler. And here we are in the opposite realm. We are trying to understand the stratification of the singular locus. So we need a version of singular. And fortunately, there is such a notion, and it's in parallel to the notion of singular Calabi-Yau. So as you know, there is Calabi-Yau. This is the smooth, the smooth version. And to this corresponds a singular version, which are Gorenstein singularities. Now, in the same way, for hyperkähler, this is also smooth, there is a singular version, which is called symplectic singularity. So here I'm glossing over some details. One of them is that we will adopt a complex symplectic view on hyperkähler manifolds. We consider them as complex symplectic manifolds, and then there is a notion of symplectic singularity. What is this notion? Roughly speaking, so this notion was introduced about 25 years ago, even though it was known and studied before, but the formalization comes from Bourget in 2000. So this symplectic singularity means you have an algebraic variety which carries a symplectic form. There is a symplectic form on the smooth locus, on the regular locus, which can be extended to a regular two-form on any resolution. So if X is a symplectic singularity, it means that for any resolution Y of X, here there is an omega, a two-form, closed two-form defined on the smooth locus here. Then you can pull back this two-form on Y, and then it will still be a regular two-form without poles. It might not be closed, so it might not be a symplectic resolution. Yes? Yes, I will now give examples. Yeah, very nice transition. So let's give some example. Maybe the most famous and studied example. Well, okay, I will give two classes of examples. So first example, C2 mod gamma, where gamma is a subgroup of a finite subgroup of SU2. So as you know, there is an ADE classification of those. And these are examples of symplectic singularities. And it's relatively easy to compute and even to generalize. If you have any symplectic singularity X, and then if you have a... It does not have to be symplectic on the resolution. It just needs to... Yeah, you can write in local coordinates, and sometimes it will be symplectic on the resolution, sometimes it will not be. If it is, it's called a symplectic resolution, and in most cases, there is no such resolution. But in this example here, there is in case A, and for D and E, I don't remember that. Yeah, exactly. So this is kind of a trivial example because I start from a smooth space, which is obviously a symplectic space, and I'm quotienting by a finite group, which is inside the symplectic group. And so that always leads to a singularity. And so those guys, exactly, these are quotient singularities. And this is a way to generate countless examples. And because of this, in this paper by Beauville, one question that he asked is actually, can you provide examples which are not quotients? So the technical way of noticing whether a singularity is a quotient or not is by computing the local fundamental group. The local pi1 is non-trivial. This is equivalent to being a quotient. So the question is, can we find examples with this pi1 equal to 0? And there is a class of examples which are nilpotent orbit closures. Mm-hmm.
Then for those, like, do you have one of those?
Yeah, which well, here, okay, I don't think we have them because here there is one more condition that I will impose is that the singularities have to be conical because there is a C-star action coming from supersymmetry as well. No, I'm looking for singularities with isolated singularities. So symplectic varieties with isolated singularities. These are those which will correspond to these elementary spaces. These are these atoms that I'm looking for. So it's exactly this reformulation, but let me just describe a little bit these examples here. Maybe, is it possible to erase this? Yes. Not so easy. Maybe I go here. So nilpotent orbit closures. So what is this? You take a Lie algebra. So say G is a Lie algebra. And then you say that you pick an element E in the Lie algebra, and you say that it's nilpotent if the adjoint action of E on the Lie algebra is nilpotent. And then you act by conjugation by the group G corresponding to the Lie algebra, say the adjoint group. This defines the nilpotent orbit of E. And nilpotent orbits, so the whole nilpotent cone, turns out to be a symplectic singularity, and there is a stratification exactly like what I drew here. So the nilpotent cone, N, is stratified into nilpotent orbits. And the stratification looks like as follows. So at the bottom, there is always the orbit of 0, the 0 element of the Lie algebra. And then there is always a unique orbit which lies above. And then all the other orbits are above that one. So that one is called the O minimal. And then there is all kind of other things that can happen here until at the top there is the maximal orbit. So there is a unique maximal orbit. There is also a unique, what's called subregular orbit, and then there is something complicated here in the middle. And then there is a minimal orbit. The reason I'm interested in the minimal orbit is because, by definition, it's the minimal. So it means that one has an isolated singularity. And because it has an isolated singularity, it means that this orbit can appear here in the Higgs branch, and this will be one of these atoms. So should I erase that? So O min. So I put the closure because I want to include the singularity. The O min technically doesn't have a 0. So O min is an isolated symplectic singularity with pi 1 equals 0. So it is with trivial local fundamental group for the Lie algebra, G different from type C. If it's type C, then it actually is a quotient. So that gives a very nice source of symplectic singularities with isolated. And then translated back to physics, physically, these correspond to elementary Higgs transitions. So in the picture that I just erased, I had this SU3 example. I draw it again. Here I said this corresponds to this U1 theory with 6 fundamentals. And this I will denote by A5. So with the lowercase letter, I indicate it's a shorthand notation for the minimal nilpotent orbit of the corresponding Lie algebra. So indeed, the minimal nilpotent orbit of SL6 is the same as the Higgs branch of that thing. And that's the invariant statement. This is the thing that goes here. And here, similarly, we had SU2 with 4 fundamentals, and here I put D4. That's the minimal nilpotent orbit for SO8, and that's what goes here. So now we can forget about this gauge theoretic description. These are the Higgsing transitions. But already here we have other examples because we have all the other algebras. So A-type and D-type, they correspond to gauge theories. But then B-type or exceptional types and so on correspond to things which cannot be written as gauge theories. So these will correspond to strongly coupled theories. And so just to give an example of that, so examples of appearance of other orbits. An example of this is if we change the dimension. Remember, this was for 4D n equal to 2 theory, SU3 plus 6 fundamentals. Now let's take exactly the same theory, but let's take it as the gauge theory phase of a 5-dimensional n equal to 1 SCFT. So in 5 dimensions, the running of the coupling constant is such that in the UV, it's a strongly coupled theory. So there exists a strongly coupled n equal 1 SCFT in 5 dimensions, which has a relevant deformation, which brings it down to a gauge theory, which is exactly that one. But that strongly coupled field theory is, has a Higgs brand which is very different from that. Because when you reach the UV and you have this coupling which is infinite, well, strongly coupled effects really kick in, and they change the geometry. In which way does it change it? Well, you could try to describe it using the language of physics, but it's very hard. And here, the point is, I can find a combinatorial object which describes it. It will be akin to that one, but different. And what it gives, if you make the computation, and I will explain right after how to compute those things, is as follows, that the diagram changes to such a diagram. And now, at Chern-Simons level 0. Yeah, thank you. So indeed, this level will change the thing. So here I put Chern-Simons level 0, and then here you have the appearance of E6 orbits, and A1, and D5, and A5. But I want to point out that there is an E6 here. That's the sign of strong coupling. We cannot describe this part just by some Higgs brands of some theory. So that's the first appearance of something new. Okay. So now, try to write here. The question is it true that every transition, like it seems, if we look at just these two examples, here it's also E6 and A1, if we look at these two examples, it seems that all the transitions, so every Higgsing is always a minimal nilpotent orbit. But this is actually not true. So are there other examples of ICSS? So this means isolated, conical, symplectic singularities. With pi1 equal to 0. That's the question. And in the paper by Beauville, he asks this question. And he has no other answer than this one, minimal nilpotent orbit. And I could draw some chronology. This is time, this is 2000. So here we have O-min, which of course was known from before, but here it is recognized as one answer to that question. And then what happened since then? Well, some additions were made quite after. So in 2003, there is the so-called quasi-minimal degenerations, which are some new examples, new answers to this question, which appear in as transverse slices in affine Grassmannian associated to C-type and G-type Lie algebras. And I will not describe what they are now for time reasons, but they will reappear at the end of the talk. And then for a while, that's it, that there is no other answer. The reason there is no other answer is because one prime source of singularities are these nilpotent orbit closure, and there is a theorem by Kraft and Procesi back in the 80s, which says that if you draw this poset, then all the transitions here for classical type, for classical G, so G of type A, B, C, D, all transitions are of type O min or C2 mod gamma. So one of these two examples. And for exceptional type, even though nilpotent orbits have been studied in the 80s as well, it was extremely hard to compute the geometry of the transverse slices. And most of them seem to be actually also O min or C2 mod gamma. The problem is that it's almost all of them, but it's all of them with two exceptions, which appear in E6 and E8 nilpotent cones. So that was done in 2015 by a team of algebraic geometers, including Barhua Fu, who was here last week, and Daniel Juteau, and Paul Levy, and Eric Summers. And they computed all the transverse slices in all Lie algebras, and they find two exceptions to that Kraft-Procesi theorem that applies to classical case. And it was a bit mysterious, so they give them names, but there's no normal, but I was not completely explicit here. I take, let's restrict to the normal ones. We can discuss non-normal. So yeah, there are only two exceptions. So there are exceptional, so slices in exceptionals, Lie algebra, nilpotent cones. Okay, and then again, these were a bit mysterious. There is one which they called chi. It was just called chi. And then the same people with some additional ones, Bonafé and Bellamy, they noticed a few years later, in 2021, that actually this chi is the first element of an infinite family, which they called YD. So that chi was actually the Y5. And then D, this is an integer D, which is larger or equal to 4. And for any D, you have a new isolated conical singularity with pi1 equal to 0. And coincidentally, at the same time, this is when we, with Amihai and others, we were trying to look in physics. And we had a physical theory, which is actually a 6-dimensional analog of this, in which we could not identify one transition. And it turns out these transitions are exactly this YD. So then the story accelerates a little bit. So in 2022, we noticed that these actually appear in physics. So in 6D, n equal 1, 0 SCFTs, these same slices appear, but we also found new ones. And then in 2023, Namikawa, inspired by this paper, finds and provides an infinite family of new isolated singularities. And finally, the result that I want to show today is, so in 2025, several new additions are made, and I will explain how. But then I also want to mention that this result that I will now describe, where we use 3D n equal 4 Coulomb branches, recovers everything from there on, with one exception, which was also found in 2025 by Callum Berry. So let's call it the Berry singularity, and that's kind of an outlier, and we don't really understand what it is. So I can just explain very briefly well, no, let me not explain. If you are interested, you can ask me, because I want just to describe this result that we obtained and which recovers everything that was done before plus new additions. Yes? Mm-hmm. Yeah. So, but then do they, so first of all, yes, I'm excluding the quotients. So they are if they are non-quotient singularities, and if they are, mm-hmm. Mm-hmm. So, well, we can try to see where it fits, but unless everyone missed them, but there must be something that doesn't fit the definition. But yeah, we can discuss later. Okay, so yeah, so now exactly, I will turn to Coulomb branches because that's another source. Actually, I could have written number 3 here. So another example. Another source of examples are Coulomb branches, are 3D n equal 4 Coulomb branches. So this comes from the fact that the 3D n equal 4 superconformal algebra has an SU2R piece, as I wrote for all the dimensions, but also an SU2C. And so the Coulomb branch is also of the same singular hyperkähler type, so they are also symplectic singularities. And it turns out that this actually recovers these minimal important orbits. So for instance, so O min of a certain Lie algebra, G, is equal to the C, so let's call it C 3D n equal 4, of a quiver gauge theory, a quiver theory with, so defined by the affine Dynkin diagram. With the ranks of the gauge groups given by the comarks of the algebra. So for instance, O min, well, okay, with my notation here, for instance, the D4 that appears over here, D4 is the Coulomb branch of the quiver, which I can denote like this, 1, 1, 1, 1. So that means you can define a gauge theory with gauge group U2, U1, etc. The links are hypermultiplets, and then you consider it as a 3D n equal 4 gauge theory. It flows in the infrared to some conformal, to some SCFT. You can compute the Coulomb branch of that, and that gives the same as the minimal nilpotent orbit. But the point is we can get more. So for instance, so using techniques from string theory, we can realize many Higgs branches as 3D n equal 4 Coulomb branches. So for instance, the one that I computed here using so this 5D n equal 1 SCFT can be obtained in string theory by either putting M theory on a toric Calabi-Yau threefold, or by putting it on a brain web, 5 brain web. And using any of those techniques, you can realize that the Higgs branch of that theory over there, so the 5D SCFT, I don't copy the definition, but that's the one over there, is equal to the Coulomb range of a particular quiver gauge theory, which turns out to be a graph like that. 1, 2, 3, 2, 1, 2, 1, 1. And then using this description, it turns out that we have developed algorithms that allow from this to extract what is the singular structure. So from this, we can extract the singular structure. So over the years, there were several different algorithms that one can apply to this in order to get the singular structure. And in view of time, I will only describe one. So the first one historically is called the quiver subtraction. So the idea is you start from the quiver here, and then you look in the quiver if you can find quivers corresponding to known singularities. So for instance, here, in this diagram, you can recognize that here there is the affine E6 diagram. Right? Actually, it appears twice because you can select this node or this node. And this is why I know that there will be two E6 singularities in the Higgs branch. And then there is also a D5. You see it here. That's a D5. That's E6. So that's one way to know. And that was a very efficient tool, and it is derived from the physics of brainwaves. The problem of this is that if you want to know what is the diagram, you need to know what to subtract. So you need to know, I recognize there is D5, I recognize there is E6. But if you didn't know that there was, if you didn't know this result, then you wouldn't know. Now, there is another algorithm, which we call fission and decay, but let's focus on fission. There is fission and decay algorithm, which we wrote with Marcus and Zhenghao, who is also in the audience. This algorithm allows, without knowing in advance what would be the possible isolated singularities, it allows to know what is the stratification without doing anything. So I will not describe the full algorithm here, but I will just describe a consequence of this algorithm. A consequence is if you find quivers with no strict positively balanced subquivers have a Coulomb branch, which is isolated conical symplectic singularities. And actually, they are all of them. So all the isolated singularities that you can realize as Coulomb branches of unitary quivers are those which satisfy this condition. So no strict positively balanced subquiver. So I need to explain a bit what this is, but that's the main consequence of the algorithm that I'm using. So what do I mean by positively balanced subquiver? Well, here, for instance, you have an example. The E6 subquiver is positively balanced. The balance is just when you have a quiver like that, you compute the number of neighbors of a node minus twice the label of the node, and this should be a non-negative number. So here, for instance, the balance is 3 plus 1 minus 2 times 2, which is 0. So that's larger or equal to 0, so that's fine. So as part of this, of course, you recover all the affine Dynkin diagrams, because the affine Dynkin diagrams are exactly those which are exactly balanced. The balance is 0 everywhere. But then there is more. And now it translates into graph theory. exercise to classify exactly all the graphs which have this property. And it turns out that this is exactly the kind of problems we like, because it turns out this is doable, but still is non-trivial. And the answer is there is a list which I will copy. What's the, 5 minutes? Okay. So, okay, so I will draw only part of the list, but you can look up my slides and you will have the full list. But so the theorem is that the complete list of quivers satisfying, let's say, this condition here is as follows. I will write it here. And I insist that this is a complete list. So it will show everything we can find using this method. And you might say, oh, that's a bit restrictive. But then, as I promised, it turns out that this list will actually contain everything which was known before, plus new things. So the list is as follows. First, it contains of course, the affine linking diagrams, which I don't copy. Then it contains a diagram of this type, which are circular quivers, like that, with decoration, so arrows on the edges, like that. And, well, I need to specify some, and these are all ones here. There are some conditions on which arrows you can put exactly, but so that's one kind. And then there are some exceptional cases which do not belong to those families. And so one such, a family of exceptions is something like that, 1, 2, 1, with 3 arrows, 2, 1, and then there is 2, 1 with this. So I didn't explain what these arrows mean, but you can think of it as defined by fixed loci of a discrete group acting on Coulomb branches of other quivers. So like this, and then there is another series. Okay. Okay, and that's it. So that's the full list. So what this means is, in one direction, the Coulomb branch of all of these gauge quivers correspond to an answer to the question by Beauville. The second point is, these are all you can find if you restrict yourself to this kind of quivers. The third point is, let's compare with what is known. So as I said, this corresponds to the minimal nilpotent orbits. Then it turns out this is exactly the infinite family of singularities found by Namikawa 2 years ago. Those one here. It turns out those ones are exactly the YD that I also mentioned here. Those two are those that I mentioned also here from 6D theories. So all of those were actually known. And then we have this. Yeah, this is also known. This corresponds to some C2 mod D type. And those are new. And those ones, there is no known construction in string theory or superconformal field theory where these appear naturally. So that's one challenge, is to find, is there a way to construct this using some natural, either geometric engineering in string theory or brain construction or something like that. So going back to the initial question, each of those singularities correspond to one kind of Higgs transition, generalizing the standard Higgs mechanism. And as far as these Coulomb branches are concerned, that's all there is, as far as unitary quivers are concerned. And this covers a large class because, as I said, for instance, if you have 5D SCFTs, it is conjectured that all of them can be realized in M-theory from local Calabi-Yau threefolds, which are of a kind called general historic manifolds or varieties. And then one can prove that in this case, there is always a realization of the Higgs branch as the Coulomb branch of such a quiver. And therefore, this is everything that can happen in 5 dimensions. So, yeah, I had prepared some, yes? Yeah, basically it means that the theory is good as a 3D theory, yeah. So that's exactly the sweet spot where it's, again, it's not that the 3 is, it's not that the balance is 0 everywhere, that it's positive, but then if you remove one thing, then it becomes negative. You can check for all of those graphs. And for instance, you see, if you try to put one more arrow here, then this is no longer, it doesn't satisfy this property, because then this one would be a subquiver, etc. So there is a graph theory you have to find. It turns out there is a very general Robertson-Seymour theory in graph theory, which tells you that for any property of that kind, there is a finite number of minima up to contraction. So that's why you have a finite number of graphs here. And so that's the mathematical, that's the graph theoretic interpretation of this. The physical one is these are all possible Higgs transitions in this particular class. Now, of course, there is a question. We know that this is not all because there is one that we did not find. So this one is the only one that does not appear in this classification. So there is a question now. Can this be realized physically? So what is the physical interpretation? Is it a Coulomb branch? These are open questions, but this dates from 1 month ago, so we don't have an answer to that. And yeah, so maybe I should stop here, but just by saying that these results give these atoms for a certain class of theories. Now, the main question that now we are trying to investigate is how can these atoms be put together to then reconstruct the theory? It's nice that we have been able to take a theory, we break it to the smallest parts, and now the question is, what is the chemistry of it? So how can you put them back together to construct physically consistent theories? And there, I think we have some ideas, but it's a largely open question. So yeah, with this, thank you.
Any question for Antoine?
Well, you can. Well, first of all, these are not really 3D theories because of the non-simply laced edge. So you can of course unfold the quiver, and then you find some 3D theory, and then you have a Z3 acting on it, and then the fixed locus of this Z3 action is isolated singularity. But that's not really a physical theory. So as far as I know, this is new. This is a new construction. So it answers conjecturally. Of course, we have to check that the pi1 is 0 and so on. But this answers the question by Beauville. But it is not clear what is the physical interpretation. All the others, they appear in physics. So is there something that prevents those to appear, or is there some construction? So in string theory, it will be a bit difficult because it has to involve some kind of orientifold on this side, but also some kind of twisted compactification. If you try to do this from 5D or 6D, for instance, Z3 twisted, but it has to live aside with the orientifold. So that's what makes the story complicated. So I don't know what to do with them. Yes.
Expectations that such that none of that will ever acceptable of that pain. Or how does this expectation fit this classification of program to classes?
Yeah, but as I said, these are not really Coulomb branches because, as you say, you say that so for the affine simply laced in diagrams, then it's really a proper Coulomb branch, and then you can indent on mass parameters and so on. Here, you can also try to do it, but these are loci in a Coulomb branch. So I don't know if you can infer from that there is no symplectic resolution. Also, of course, there are symplectic resolutions for other cases, but if we include, well, I erase now, but if you include quotients, then there are constructions. For instance, when you take C to the 2n mod by some crystallographic quaternionic reflection group, then there is this classification, and then some of them admit resolutions, some symplectic resolutions, some of them do not. In some cases, it's still an open problem, so I think it's very hard to know. The answer is not known there, at least for the quotients. So those won't have, but isolated can be hidden in them. So actually, that's how he found it here. So here, the construction starts from, you take C4, mod by the G5. So this is the fifth of the Shepard-Todd classification. This is indeed not isolated. Then you blow up. And then in one of the charts covering the blow up, there is an isolated one. It's unclear why it's hidden there, and it's completely unclear what is the systematic of this construction. But I should say also that these ones also arise this way. If you take a C4 mod dihedral group, you do blow up, and then you find that those guys appear. So I think it's a completely open question. This technique only appeared a few years ago, and only 2 examples are computed in the complex reflection group. There's G4 and G5. So all the rest is open.
Okay, so we are out of time, so let's thank Antoine again.